Right everyone, today we're going to be going through A-level biology required practical number 11, which despite its intimidating sounding name is relatively straightforward and you should be used to this sort of stuff by now. So the title is Production of a Dilution Series of a Glucose Solution and the Use of Colorimetric Techniques to produce a calibration curve with which to identify the concentration of glucose in an unknown urine sample. That's a lot of very big sounding words. Very simply put, we have a series of glucose concentrations that I have pre-made. So we've got 10, and these are in millimolar or millimoles per decimeter cubed, depending on whatever you want to call it. And I've got 10, 8, 6, 4, 2, and 0. So those are our known concentrations of glucose. And the framework for this is an investigation into potential diabetes or diabetes mellitus. Now, historically, one of the ways that people used to not necessarily diagnose diabetes, but certainly was an indication of diabetes, was, the name itself, diabetes mellitus, the Latin name for, or Greek maybe, comes from the sort of amalgamation of words that literally mean sort of high volume and sweet tasting, which is a reference to patients' urine. So it's a sort of known thing that people who have diabetes urinate quite a lot compared to non-patients. And it's not pleasant to think about, but their urine is quite sweet tasting compared to normal. Sometimes sort of measurably so with human taste, which is not nice to think about. So there was a diagnostic technique which was literally dip your finger in a pot of urine, and if it tasted sweet, then you've got to start considering diabetes, which is obviously not particularly pleasant, but oh well. And patients who have diabetes, because of their increased glucose levels in their blood very often, that does seep out into the urine. And I believe the sort of normal level of glucose, which is naturally excreted at times in human urine, is something like 0 to 0.8 millimolar. So basically, anything that you can get above 1 millimolar is cause for concern. Now, that's not to say that everyone who has over 1 millimolar is definitely diabetic. There are pre-diabetic and there are various potential solutions or problems there. So basically anyone who's above, I think the average is about 6 millimolar, is probably most likely a diagnosed diabetic who really should be undergoing treatment. But anything below that, it's certainly something you want to consider if you're making a medical diagnosis. So that's the sort of framework we have for this practical, and as such we have 3 down here of our unknown urine samples labelled T, D and H, and our 3 sort of mystery samples are sort of allegedly from patients named Tom, Dick and Harry. I didn't write the spec, someone else did. They have a very funny sense of humour. So as you might remember from your first year studies, glucose reacts with Benedict's reagent to produce it changes colour from a sort of this sort of dark-ish blue through sort of yellows and greens, sometimes browns, and into a sort of brick red or orange precipitate. And that's a very sort of obvious, easy visual clue. But however, that's not going to be quite enough for our uses here, because that particular type of Benedict's reagent is qualitative, meaning that it's a relatively simple yes, no, does it have glucose, does it not, or doesn't it? So it's not really that helpful when you're trying to make a sort of quite accurate calibration curve for precise concentrations. So the stuff I have here in these 9 test tubes is quantitative Benedict solutions. A slightly different formula, similar sort of original or starting colour. But in this case, it decolorizes. So it goes from a sort of blue to effectively clear with some white precipitate settling out. And more importantly, it precipitates out and decolorizes proportionally to the concentration of glucose. So the more glucose, the more the discoloration. And the way we're going to measuring that sort of in a quantitative way is using our colorimeter here, set to, I believe, 680 nanometers. So very simply what we're going to do is I'm going to be taking these 6 known samples, adding an equal quantity of them, so I think it's 2 centimeter cubed, to our 6 knowns, and then we're going to be doing the same with our unknowns. There's a water bath off screen, which is set to I think 85 or 90 degrees, and then leave it for 4 minutes, which I'll hopefully be able to cut out. And then by the time we get back, hopefully, there'll be a nice, maybe not linear, but certainly predictable calibration curve, which we can then sort of use. So we'll plot our graph and we'll plot the calibration curve, and then we can use either the formula of that graph or the sort of visual representation of that graph to then, if you find your, your absorbance after you've reacted, our Tom sample is really relatively similar to an 8 sample, then you can logically deduce that Tom's sort of urine glucose concentration is about 8. It's pretty straightforward and it should work reliably. Right, and we're back. Just to make sure I was labelling my test tubes properly. So I am just going to be, I'll go to hear it, I'm going to be rinsing out my pipette in between each sample to try and minimise cross-contamination. So we've got our 8 here. That's approximately 2 there. Oops, lost a drop there. 8. We've got our 6 sample. Plus 6 back. And we've got, where's 4 and 4. As I say, although you can't see it, I am making sure that the meniscus is reading properly for each of these. We've got our 2. The reason I've got so much of the glucose sample is in case I need to run some repeats. So I think I've got 10 centimetre cubed of each one, which means in theory I can run up to 5 repeats, although I'll likely be running 3 just for the sake of workload. And then finally our 0, which is in fact, as you may have guessed, just distilled water. So I could just put in some distilled water, but I'll try and be proper about it. So we're not expecting any change from this, well, hopefully, unless thermal degradation just happens. And then last but not least, we have our Tom, Dick and Harry. It's got remarkably clear urine. Right, well hydrated, what can I say? 2 centimetre cubed in there. And I'm going to just swirl these around to make sure they're nice and mixed, although I don't predict that being a problem. Oops, D&H there. Where's Dick? There we go. It doesn't really matter, but it's all the same Benedict, but making sure it's all properly labelled so I don't get confused. 2 there. And then finally we have Mr. Harry. Yeah, okay. Right, so that is our calibration curve. Oops, just trying to focus there. Calibration curve samples all labelled properly, and our 3 unknowns, calibration sample. And I'm going to now put them in our water bath for 4 minutes. I'm going to stop the recording because you need to see all this. And then I'll be back when they've all reacted. Right, everybody, so I've just finished a second round of results for this experiment. So you've just seen me place these test tubes in the water bath for 4 minutes. And what has happened is, when I did that, I then proceeded with that experiment collected some results and found they weren't adding up right. And I've had some time to think about it, and I figured out what my problem was. So what I was doing is I was taking the result, or the test tubes from the water bath, these fresh, hot, 80 odd degree test tubes, and then putting them here, and then immediately sampling them into our cuvettes, which were here, and then reading them like that. So all of our data came from hot, which is kind of important, but more importantly, from test tubes that still had the precipitate in them. So I may have mentioned earlier, when you have a quantitative Benedict, so your qualitative Benedict has that red end stage precipitate production when it's in contact with glucose or reducing sugars. Quantitative, the stuff we're using today, produces a white milky precipitate when the Benedict becomes decolorized. Now, I hadn't accounted for the fact that because these tubes were still hot and still fresh, there hadn't been enough time for the precipitate to settle out and settle to the bottom. So I'm not sure if it's really that visible, but you might just be able to see that there is a sort of white powder, maybe just at the edge there, that has now settled in these ones. And that still suspended sediment or precipitate was really affecting our results, and it was really throwing up some wacky numbers and didn't give good results. So that's my fault. I didn't anticipate that there would still be sediment or precipitate floating about and blocking the light and giving us erroneous results. So now I've got these redone test tubes, and I'm not going to bother with cuvettes this time because it's running out of light and I need to leave at some point. So I'm just going to make sure that each of our test tubes, when we put them in, has been thoroughly dried with a paper towel, so I'm not putting anything moist in there. And I have found that using a distilled water, so in this case it's our 0% glucose original urine sample, gives you the best results at 680 nanometers. So I'm just going to put it in there, I'm going to reference it, and that should come up as 0. Sorry, more paper towel. And I'm going to proceed with the results. So I'm going to draw up a quick results table if my pen's gone. So we have our sample, and then we've got our absorbance. So we're going to go 0 sample, 2, 4, 6, 8, 10. Tom, Dick, Harry. Just very brief. Don't do this in your actual work. This is just me up against the clock doing a very hasty results table. So we've zeroed our colorimeter. Let's see what kind of results we get now. So we're going to start off with our calibration curve. So sorry, that goes there. So we've got our 0 sample. Gives us a reading of 1.77. And then 2. Make sure this is dry. .52. 4. So this is already better results than we got last time, because there was a weird spike in the middle that was just me not accounting for that sediment. Now, if we were to be really, really thorough, we could decant the solution on top of the sediment, or the precipitate, and measure it that way. But because our colorimeter fires light through the sample at sort of, on this test tube it would probably be about there. If the sediment's completely located at the bottom of the test tube, I don't think it's going to affect our results whatsoever. 0.67. So already that is a much more linear progression than the results you haven't seen showed. So we've already got a nice sort of calibration curve and got our results there, which I will then plot on a graph and make available for your teachers. And then we're going to go through our Tom, Dick and Harry measurements. .47. Let's get some of that. is 0.96. And last but not least, Harry, sorry, just every time I take it off camera, I am just drying it off. And then last but not least, 1.74. So that, just straight away, looks like a lot neater set of data than I had beforehand. So apologies for the sort of disruption to continuity, but I couldn't let my poor scientific methodologies affect the results of the experiment. And I will repeat this a couple of times just so we've got at least 3 sets of data to make an average of, and then that will hopefully inform a much more accurate and repeatable and reliable experiment. So I will get to it. I'll produce 2 more sets of data and then we'll average them out, and then hopefully that data will be made available to you by your teachers. So that has been RP11, or at least after I fixed my errors. Anyway, see you around.